Welcome back. This is part 3 of the RC time constant lab. And what I'm going to do in this final part of the lab is to examine the exponential decay and model it according to an exponential decay e to the minus alpha t, where alpha is some constant. We found in the last part that this part of the curve, the charging part of the curve, has actually shows all the signs of an inverse exponential, i.e. it's a e to the a, the quantity 1 minus e to the rt plus b. We found that the r is actually 1 over the time constant. We found that time constant to be nearly 1. It was 1.05. And what I'd like to do now is look at this part of the curve, pull that into a curve fitting program, and go ahead and see if the time constant here matches the time constant here. They should match, since the resistor and capacitor are pretty much the same quantity. Alright, so let's get started. I have here my graph of my charging and discharging. The discharging section starts at about 12 seconds and goes all the way down to about 18, let's go 19 seconds, just to keep the numbers round. So let's go ahead and go back. I'm going to get rid of my my IO lab design, and I'm going to go back to the spreadsheet. Here we are, and I want to pick again from region 12 seconds to about 19 seconds. So let's go ahead and scroll down and to about 12 seconds. So here we are. This is where things start to decay. Well, it's not decaying just yet. It doesn't start decaying until here. So to about 12.11 seconds. So I'm going to grab all the data from here to about 19 seconds. And I'm going to put that back into my curve fitting application, Logger Pro in this case. And so we're just going to go ahead and scroll. Notice if you look at the figures at the last column, column C, notice how the numbers have become smaller and smaller as we go. Alright, I have my column selected, edit, and I'm going to copy this, and I'm going to launch my Logger Pro so that I have it. And it will take a couple seconds. There we go. And once again, it's just a question of copying and pasting. So I'm going to paste my data now in here. And you can see I have my column. Once again, I'm going to rename my columns. This is for time, t, seconds, done. This is the voltage across the resistor, or Vin. I'm not terribly interested in that, so we might not do a lot with that, but let me just go ahead and label it anyway. Volts. And then, of course, my last column, the blue column, is the one I'm really interested in. This is voltage across VC, volts, and we'll go ahead and click done. So now I have my 3 columns. The one I'm interested in again is the blue column, VC. So I'm going to select on my graph voltage across capacitor, and you can see the exponential decay. Now there's a couple of ways of doing this, and I'm going to show you one way, and then maybe if I get a chance, do one more. So here's my curve, and I'm going to go ahead and grab the data. So I'm going to select what I want to look at, and I'm going to do a curve fit and say, okay, this is e to the minus ct plus b, the natural exponent, and try the fit, and I see I get a perfect fit. And so let's make that a little bigger so you can see it. There we go. And so you can see the time constant in this case is 1.021. That compares with 1.05 by about 0.03. So the percent difference is absolutely tiny. So we're actually in really nice shape as far as the time constants being about the same.